Tonight, we're going to explore something that sounds simple, but reveals just how trapped we really are. We're going to answer one straightforward question. How long would it actually take us to travel 1 light year, not in theory, not with imaginary technology, but with what we have right now? And by the end of tonight, you're going to understand why the stars might as well be painted on the ceiling of a cage we can never escape. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what a light year actually is, because most people misunderstand this from the beginning. A light year isn't a measure of time. It's a measure of distance. It's the distance light travels in 1 year. And light moves incredibly fast, almost beyond human intuition. Light travels at about 186,000 miles per second. In just 1 second, light could circle Earth's equator about 7.5 times. In a single second, light travels farther than most people will travel in their entire lives. Let that sink in for a moment. In the time it takes you to blink, light has already crossed a distance equal to 3 trips around the entire planet. Now imagine multiplying that speed by the number of seconds in a year. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. Multiply those together and you get about 31,536,000 seconds in 1 year. Light traveling at 186,000 miles per second for about 31,558,000 seconds covers a distance of roughly 5,870,000,000,000 miles. And here's the critical question we're exploring tonight. How long would it take us to travel that distance? Let's start with the fastest object humanity has ever built. The Parker Solar Probe. Launched in 2018. The Parker Solar Probe is a NASA spacecraft designed to study the Sun. It's designed to dive closer to the Sun than any spacecraft in history, passing through the Sun's outer atmosphere, the corona, to collect data about the solar wind and the Sun's magnetic field. To survive that environment without melting, the spacecraft has to move incredibly fast. At its maximum speed, the Parker Solar Probe reaches about 430,000 miles per hour. That makes it the fastest human-made object ever built. For comparison, a bullet fired from a high-powered rifle travels at roughly 2,800 miles per hour. That means the Parker Solar Probe is moving more than 150 times faster than a speeding bullet. And yet, even at that speed, it is still painfully slow compared to light. Light travels about 670 million miles per hour. In other words, light moves roughly 1,560 times faster than our fastest spacecraft. So the question becomes clear. How long would it take the Parker Solar Probe to travel 1 light year? 1 light year is about 5,870,000,000,000 miles. At a speed of 430,000 miles per hour, that journey would take about 1,560 years. Let's put that into perspective. That's roughly the time from the fall of the Roman Empire in the year 476 to the present day. In other words, nearly the entire span of the Middle Ages and the modern era combined. And that's just to travel 1 light year. To reach Proxima Centauri, the nearest star to our Sun, located about 4.25 light years away, it would take more than 6,600 years. By the time it arrived, humanity would either be extinct, evolved into something unrecognizable, or spread across the galaxy with technology that makes the Parker Solar Probe look like a wooden cart. Or maybe we'd still be here on Earth, having forgotten we ever launched it. Now, you might be thinking, well, the Parker Solar Probe wasn't designed to travel to other stars. It was designed to study the Sun. What if we built something specifically designed for interstellar travel? What if we used our best rocket technology and optimized everything for speed? Let's look at the Voyager probes. Voyager 1 and Voyager 2 were launched in 1977. They're both still operational, still sending data back to Earth after more than 45 years in space. Voyager 1 is currently the most distant human-made object from Earth. It is about 14.12 billion miles away, far beyond the orbit of Pluto, now traveling through interstellar space, the vast region between the stars. Voyager 1 is moving at about 38,000 miles per hour relative to the Sun. That is much slower than the Parker Solar Probe. But by everyday human standards, it is still extraordinarily fast. At that speed, Voyager 1 could travel from Los Angeles to New York in about 4.5 minutes. But how long would it take Voyager 1 to travel 1 light year, at a speed of about 38,000 miles per hour? The journey to 1 light year would take roughly 17,600 years. That is more than 11 times longer than the time it would take the Parker Solar Probe to cover the same distance. The Voyager probes remain one of the most remarkable technological achievements ever created by humanity. They've lasted longer than anyone expected. They've sent back images and data from Jupiter, Saturn, Uranus, Neptune, and now from interstellar space itself. But they're slow. Let's try something different. What if we used nuclear propulsion? Nuclear rockets have been studied extensively. The basic idea is to use a nuclear reactor to heat propellant to extremely high temperatures and expel it out the back of the spacecraft. One concept that could theoretically achieve far higher speeds than chemical rockets is nuclear pulse propulsion. In the 1950s and 1960s, scientists proposed a project known as Project Orion. The idea was radical. Instead of using a conventional nuclear reactor, the spacecraft would detonate small nuclear bombs behind it. Each explosion would push against a massive shock absorber plate, propelling the spacecraft forward with enormous force. It sounds insane, and in many ways it is. But the physics behind the concept actually works. Calculations suggested that an Orion-style spacecraft could potentially reach speeds of about 3 to 5% of the speed of light. If we take the optimistic estimate of 5% of the speed of light, then traveling a distance of 1 light year would take roughly 20 years. For the first time, interstellar travel begins to sound not impossible, but conceivable. That's within a human lifetime. If you left Earth at age 25, you'd arrive at your destination at age 45, still young enough to explore, still young enough to contribute to a new colony, still young enough to see the results of your journey. But here's the problem. Project Orion was never built. It was studied extensively. Engineers worked out the details. They calculated the size of the bombs, the mass of the shock absorber, the trajectory through space. They figured out how to protect the crew from radiation. They designed life support systems. But it was never built, and it probably never will be. At least not with nuclear bombs. The main problem is political and practical. Launching nuclear weapons into space is banned by international treaty. The Partial Test Ban Treaty of 1963 and the Outer Space Treaty of 1967 both prohibit nuclear weapons in space. Even if those treaties didn't exist, the technical challenges are enormous. You'd need to carry thousands of nuclear bombs with you. Each one would need to be perfectly timed and positioned. A malfunction could destroy the spacecraft. The radiation exposure for the crew would be significant even with shielding, and the cost would be astronomical. So, Project Orion remains a fascinating idea. A theoretical possibility. But not something we're actually going to build anytime soon. What about other forms of nuclear propulsion? There's something called nuclear electric propulsion. This uses a nuclear reactor to generate electricity, which then powers an ion drive or similar electric thruster. Ion drives work by accelerating ions charged particles to very high speeds and expelling them out the back of the spacecraft. The thrust is tiny, but it's continuous. And over time you can build up impressive speeds. NASA's Dawn spacecraft, which explored the asteroid Vesta and the dwarf planet Ceres, used ion propulsion. It was powered by solar panels, not a nuclear reactor. But the principle is the same. The Dawn spacecraft achieved a total change in velocity of about 25,000 miles per hour over the course of its mission. That is impressive for a spacecraft with such a limited size and power supply. But it is still far too slow for interstellar travel. Even if a much larger nuclear reactor were used to provide more electrical power, nuclear electric propulsion would likely reach speeds of only about 1 to 2% of the speed of light at best. At 1% of the speed of light, traveling a distance of 1 light-year would take about 100 years. That is longer than a human lifetime. A mission like that would require multiple generations of travelers. The crew who depart from Earth would know that their grandchildren might be the ones who finally arrive at the destination. This idea is known as a generation ship, and it raises a whole new set of challenges for human survival, society, and long-term life in deep space. How do you maintain a closed ecosystem for 100 years? How do you prevent the spacecraft from slowly breaking down over such a long period of time? How do you maintain social cohesion when every member of the crew knows they will die before reaching the destination? And how do you prevent genetic problems caused by inbreeding within a very small population? These problems are not impossible, but they are extremely difficult. And so far, humanity has not solved them. So, nuclear electric propulsion might allow us to reach about 1% of the speed of light. Perhaps 2% if we are optimistic. Even at that speed, traveling 1 light-year would still take roughly 50 to 100 years. What about fusion propulsion? Nuclear fusion is the same process that powers the sun. It happens when hydrogen nuclei are forced together under extreme temperature and pressure until they fuse into helium, releasing an enormous amount of energy in the process. We've been trying to build practical fusion reactors on Earth for decades. We've achieved fusion in laboratories. We've even achieved net energy gain where the fusion reaction produces more energy than it took to start it. But we still don't have a working fusion power plant. The engineering challenges are immense. You have to contain plasma at temperatures of millions of degrees. You have to maintain that containment long enough for the fusion reactions to produce useful energy. You have to extract that energy efficiently. It's difficult and we're still working on it. But let's assume we solve it. Could we use fusion for spacecraft propulsion theoretically? Yes. A fusion rocket would heat propellant to incredible temperatures using fusion reactions and expel it at extremely high speeds. If a spacecraft could continuously accelerate using fusion propulsion at a reasonable rate, it might be able to reach speeds of about 10 to 20% of the speed of light. At 10 to 20%, traveling a distance of 1 light-year would take roughly 5 to 10 years. Suddenly, interstellar travel begins to look almost practical. 5 years is still a long journey, but it is within the range of missions humans have already experienced in space. Astronauts have already spent more than 1 year in space during a single mission. A journey lasting 5 years would certainly be difficult, but it would not be completely beyond human capability. But here is the reality. We do not yet have fusion propulsion. In fact, we do not even have fully operational fusion power plants on Earth. Building a fusion rocket capable of accelerating to 10 or 20% of the speed of light would require solving all the challenges of fusion energy first, and then overcoming additional obstacles such as reactor miniaturization, radiation shielding, propellant storage, and entirely new spacecraft designs. It is probably decades away at minimum, and possibly centuries. So fusion propulsion is theoretically possible. But in practical terms, we are nowhere close to achieving it yet. Now let us move to the most speculative ideas. What if a spacecraft could travel at a significant fraction of the speed of light? Not 5, 10, or 20%, but perhaps 50% or even 90% of the speed of light. Over the years, scientists have proposed several concepts that might make such speeds possible. One of the most famous ideas is antimatter propulsion. When matter and antimatter come into contact, they annihilate each other completely, converting their entire mass into energy. According to Einstein's famous equation, energy equals mass times the speed of light squared, written as E equals mc squared. This is the most efficient energy conversion process known in physics. If 1 kilogram of antimatter were to annihilate with 1 kilogram of normal matter, the reaction would release about 180 times more energy than the energy produced when 1 kilogram of hydrogen undergoes nuclear fusion. If we could harness that energy for propulsion, a spacecraft could theoretically reach extremely high speeds. Some estimates suggest that antimatter-powered rockets might reach 70 to 80% of the speed of light. At those speeds, traveling a distance of 1 light-year would take only about 15 to 17 months. By interstellar standards, that would be remarkably fast. At those speeds, a spacecraft could reach Proxima Centauri in about 5 to 6 years. Stars located dozens of light-years away might become reachable within a single human lifetime. But there is a problem. In fact, there are several problems. First, we cannot currently produce antimatter in meaningful quantities. Antimatter can be created in particle accelerators, but only in extremely tiny amounts. Facilities such as those at CERN produce roughly 1/1000th of a gram of antimatter each year, which is far too little for any practical propulsion system. At that rate, it would take about 100 billion years to produce just 1 gram of antimatter. That is far longer than the current age of the universe. The second problem is storage. Antimatter is incredibly difficult to contain because it annihilates instantly when it comes into contact with normal matter. That means you cannot simply store it in a physical container. Instead, it has to be trapped using powerful magnetic fields, suspended inside an almost perfect vacuum so that it never touches the walls of the containment system. We can currently do this for individual particles or very small clusters of antimatter. But scaling that technology up to the kilograms or even tons that a spacecraft would require is far beyond anything we can achieve today. The third challenge is how to use the energy efficiently. When matter and antimatter annihilate, a large portion of the released energy appears as gamma rays and neutrinos. Both of these are extremely difficult to capture or redirect, which makes it very challenging to convert that energy into controlled thrust for propulsion. You might only be able to use a fraction of the energy effectively. Fourth, even if you solved all these problems, the spacecraft would need enormous shielding to protect the crew from radiation. At high fractions of the speed of light, even tiny dust particles in space become dangerous. A grain of sand hitting your spacecraft at 80% the speed of light would release energy equivalent to a large bomb. You'd need meters of shielding, which adds mass, which requires more fuel, which adds more mass. It's a vicious cycle. So antimatter propulsion is theoretically possible, but practically it's science fiction. We're not close to building it, and we might never be. What about concepts that don't require carrying your own fuel? There's an idea called a laser sail or light sail. The basic concept is simple. You build a spacecraft with a large, thin, reflective sail. You shine a powerful laser from Earth onto the sail. The photons from the laser bounce off the sail and transfer momentum, pushing the spacecraft forward. Because the spacecraft would not need to carry its own fuel, it could be extremely light. That means even a small transfer of momentum could produce significant acceleration. One concept exploring this idea is called breakthrough starshot. The proposal is to build thousands of extremely small spacecraft, each weighing only 1 or 2 grams, equipped with light sails that are a few meters across. Powerful ground-based lasers would then accelerate these tiny probes to about 20% of the speed of light. At that speed, the probes could reach Proxima Centauri in roughly 20 years. They would fly past the star system, capturing images and scientific measurements, and then transmit the data back to Earth. The signals carrying that data would take another 4 years to travel back across space before we receive them. So, the total mission from launch to receiving data would be about 24 years. This is genuinely exciting. It's theoretically possible with technology that's not too far beyond what we have now. But there are significant challenges. The lasers would need to be incredibly powerful, combining the output of many individual lasers to create a beam strong enough to accelerate the probes. The targeting would have to be extraordinarily precise. The light sails would need to be incredibly lightweight and highly reflective. The spacecraft would also have to survive intense laser heating during the acceleration phase. Perhaps the most significant limitation is the size of the probe itself. A spacecraft that weighs only 1 gram cannot carry much equipment or large power systems. It would essentially contain a small camera, a transmitter, and very little else. Another challenge is that the probe would not be able to slow down when it reached its destination. Instead, it would simply fly past the star system at about 20% of the speed of light, capturing images and measurements for only a few minutes before continuing onward into deep space. Even so, breakthrough starshot remains one of the most realistic concepts currently proposed for interstellar exploration. It's actually being worked on. Engineers are building prototypes. They're testing materials. They're calculating trajectories. It might actually happen within the next few decades. But even with laser sails, reaching 20% the speed of light, traveling 1 light year would still take 5 years. And that's assuming everything works perfectly. So let us step back and look at what we have learned. With our current fastest spacecraft, the Parker Solar Probe, traveling a distance of 1 light year would take about 1,560 years. With the Voyager probes, the same journey would take roughly 17,600 years. With a theoretical system such as nuclear pulse propulsion, similar to the concept proposed in Project Orion, the trip might take only about 20 years. However, despite the physics being feasible, we are not currently building such a spacecraft. With nuclear electric propulsion, it would take 50 to 100 years. And we don't have that technology yet. With fusion propulsion, it might take 5 to 10 years. But fusion reactors don't exist yet. With antimatter propulsion, it might take 1 to 2 years. But antimatter production and storage are far beyond our capabilities. With laser sails, it might take 5 years for a tiny probe weighing 1 gram. But even that technology is still experimental. The reality is sobering. We cannot travel to the stars with current technology. We can barely leave our own solar system. Voyager 1, after 45 years of travel, is only 2 light years from Earth. So far, Voyager 1 has traveled only about 2/10,000ths of a light year from Earth. At the spacecraft's current speed, traveling a full distance of 1 light year would take roughly 17,600 years. The stars are so far away that even light, the fastest thing in the universe, needs years to travel between them. And compared with light, our spacecraft moves so slowly that the journey begins to feel almost unimaginable. 1 light year might as well be infinity. We can't cross it in any practical sense. Not in a human lifetime. Not in many human lifetimes. The astronomer Carl Sagan once said that the cosmos is all that is, or ever was, or ever will be. But for us, for humanity as we exist now, the cosmos might as well be just our solar system. The stars beyond are beautiful to look at. They're fascinating to study. But they're not places we can go. They're not destinations. They're just lights in the sky, forever out of reach. This is the harsh reality of the universe we live in. The distances between stars are so vast that they're effectively impossible with anything remotely resembling current technology. Even with optimistic projections of future technology, traveling 1 light-year would take years at minimum, possibly decades or centuries. Now, this doesn't mean interstellar travel is impossible forever. Technology advances. We've gone from the Wright brothers' first flight in 1903 to landing on the moon in 1969. That's only 66 years from the first powered airplane to humans walking on another world. Maybe in another century or two, we'll have fusion drives or antimatter engines, or something we haven't even imagined yet. Maybe we'll figure out how to build generation ships that can sustain human populations for thousands of years. Maybe we'll develop artificial intelligence that doesn't need life support and can travel for millions of years without concern. Maybe we'll discover new physics that allows faster than light travel, though that seems extremely unlikely given our current understanding. But with what we have now, with what we'll have in the foreseeable future, the stars remain out of reach. 1 light-year is an almost unimaginable distance, and the nearest star is more than 4 light-years away. To understand how vast that is, consider another perspective. The fastest speed any human has ever traveled occurred during the Apollo 10 mission in 1969. During re-entry, the command module reached about 24,791 miles per hour, which is roughly 6.89 miles per second. At that speed, traveling a distance of 1 light-year would take about 27,000 years. The astronauts on Apollo 10 moved faster than any humans before or since. Yet even at that record speed, they would still need 27,000 years to cross just 1 light-year of space. To put that into perspective, 27,000 years ago, the ancestors of modern humans had not yet fully evolved. Our distant ancestors were still small primates living in trees. The entire evolutionary journey from those early primates to modern humans would have to unfold with all the ice ages, all the adaptations, and all the slow changes of evolution. And even then, the spacecraft still would not have reached its destination yet. This is the scale we're dealing with. This is why 1 light-year might as well be infinite. Some people find this depressing. The idea that we're confined to our solar system, that the stars are forever beyond our reach, that the universe is so vast and we're so slow. But there's another way to look at it. Our solar system is actually much larger than most people imagine. Earth may be tiny, but the solar system extends far beyond the planets. The Kuiper belt, where Pluto orbits, lies about 4 billion miles from the Sun. Beyond that region is the scattered disk, which stretches outward to roughly 9 billion miles from the Sun. And even that is not the true boundary. Far beyond those regions lies the Oort cloud, a vast spherical shell of icy objects surrounding the solar system. Scientists estimate that it may extend out to about 1 light-year from the Sun, and possibly even 2 light-years. The Oort cloud is still gravitationally bound to the Sun, still part of our solar system. So our solar system might actually be about 2 light-years across. That's a lot of space. There could be millions or billions of objects in the Oort cloud. We've barely begun to explore the outer solar system. We've sent probes to the planets. Yes, we've studied Jupiter and Saturn and their moons. We've flown past Pluto. But the vast majority of the solar system remains unexplored. There could be undiscovered dwarf planets out there. There could be unusual objects with strange orbits. There could be resources we haven't imagined. Maybe instead of trying to reach other stars, we should focus on thoroughly exploring and utilizing our own solar system. Maybe there's enough here to keep humanity busy for thousands of years. We could build habitats on asteroids. We could mine the moons of Jupiter and Saturn for water and minerals. We could establish research stations throughout the outer solar system. We could study the Oort cloud and the Kuiper belt. We could create a civilization that spans the solar system with billions of people living in space habitats on terraformed moons on artificial worlds. And maybe centuries from now, when we've fully developed our solar system, when we've advanced our technology far enough, we'll be ready to take the next step. We'll build generation ships powered by fusion or antimatter. We'll send them to nearby stars, knowing the journey will take decades or centuries, and humanity will slowly, patiently spread to other stars, one system at a time, over thousands or millions of years. But that's a long way off. For now. For our lifetimes. For our children's lifetimes. Probably for our grandchildren's lifetimes. We're confined to this solar system. And when you ask how long it would take to travel 1 light year, the honest answer is too long. Far too long for any practical purpose with current technology. Too long for a human lifetime. Too long for many human lifetimes. The universe is vast and we are slow. The stars are distant, and 1 light year might as well be forever. But we're here. We're on Earth, orbiting our sun in our solar system. And maybe that's enough. Maybe for now. Home is enough. Let me leave you with one final thought. The speed of light is often called the cosmic speed limit. Nothing can travel faster than light, according to our current understanding of physics. And light takes 1 year to travel 1 light year by definition. If we could somehow travel at the speed of light, which we can't because anything with mass would require infinite energy to reach light speed. But if we could, traveling 1 light year would take 1 year. But here's something strange. From the perspective of the traveler, time dilation effects mean that the journey would seem shorter. At 99% of the speed of light, time would slow down dramatically because of the effects predicted by Einstein's theory of relativity. A journey that lasts 10 years from Earth's perspective might feel like only about 1.4 years for the traveler on board the spacecraft. At 99.9% of the speed of light, that same 10-year journey would feel like only about 5 months to the traveler. And at 99.99% of the speed of light, the experience of time could shrink to only about 2 weeks on board the spacecraft. If it was somehow possible to travel at exactly the speed of light, then from the traveler's perspective, no time would pass at all. From the point of view of a photon, the journey from one side of the universe to the other would appear instantaneous. Of course, reaching the speed of light is not possible for objects with mass. And in reality, we may never even reach 99% of the speed of light. The energy required would be enormous. And the engineering challenges are far beyond anything we can currently imagine building. But it's interesting to think about. The universe puts fundamental limits on how fast we can travel. Those limits make the stars unreachable with current technology. They might make the stars unreachable forever. Or they might just mean we need to be patient to develop our technology slowly, over centuries or millennia, until we're ready. Either way, the answer to how long it would take to travel 1 light year is clear. With the technology we have today, the journey would take more than 1,000 years. With optimistic future technology, it might take decades or perhaps centuries. And with extremely advanced technology that may never actually exist, the journey could be reduced to years or even months. But no matter how we imagine it, the stars remain incredibly distant. 1 light year is still an almost unimaginable distance. And for now, we remain here on this small blue world, looking up at lights we can see but cannot touch. The universe is beautiful. The stars are magnificent. But they're far away. So far away that 1 light year might as well be the edge of reality itself. Thanks for staying with me through this journey. The question was simple, but the answer reveals something profound about our place in the cosmos. We're bound to our solar system by the vast distances of space and the limitations of physics. The stars are there, We can see them. We can study them. But we can't reach them. Not yet. Maybe not ever. And in that limitation, there's both humility and wonder. Humility because we're reminded how small and slow we are. Wonder because the universe is so vast, so full of places we can imagine but never visit. At least not in our lifetimes. 1 light year. A simple unit of distance. But crossing it would take longer than human civilization has existed. And that's the reality we live with. That's the cage of distance and time that binds us to this corner of space. And maybe that's okay. Maybe being here on Earth in this solar system is enough because home isn't measured in light years. Home is measured in moments in the people and places that matter to us. And our home. This solar system, this Earth, is right here. Not 1 light year away. Not 1,000,000 years of travel away. Right here. And sometimes right here is exactly where we need to be. But let's dig deeper into why this distance is so impossible. Let's talk about the physics that makes 1 light year such an insurmountable barrier. It's not just about building a faster engine. It's about fundamental limitations built into the fabric of reality itself. When we talk about traveling close to the speed of light, we're not just talking about engineering challenges. We're talking about energy requirements that boggle the mind. Einstein's theory of special relativity tells us that as you approach the speed of light, your mass effectively increases. The closer an object moves toward the speed of light, the more energy is required to accelerate it further. At 90% of the speed of light, the effective mass of the object becomes about 2.3 times its normal rest mass. At 99% of the speed of light, the effective mass rises to about 7 times the rest mass. When the speed increases to 99.9% of the speed of light, the effective mass grows to roughly 22 times the rest mass. And at exactly the speed of light, the effective mass would become infinite, which is why objects with mass cannot reach that speed. This means the energy required to accelerate you to light speed also becomes infinite. It's not just a practical impossibility. It's a fundamental impossibility according to the laws of physics as we understand them. You cannot reach the speed of light if you have mass. Only massless particles like photons can travel at light speed. And light itself always travels at the speed of light. It cannot go slower. And it cannot go faster. From the moment a photon is created to the moment it is absorbed, it moves at that same constant speed. So if we cannot reach the speed of light, what is the fastest speed we could theoretically achieve? To explore that, we need to think about energy. In classical physics, kinetic energy is equal to 1/2 times mass times velocity squared. That means if you double the speed, you need 4 times more energy. If you triple the speed, you need 9 times more energy. But this simple formula begins to break down as you approach the speed of light. At relativistic speeds, the energy required rises far more dramatically. To accelerate 1 kilogram to 10% of the speed of light requires about 4.5 times 10 to the 14th joules. That is roughly equal to the energy stored in 10,000 kilograms of gasoline. To accelerate 1 kilogram to 50% of the speed of light requires about 1.3 times 10 to the 16th joules, which is comparable to the energy in 300,000 kilograms of gasoline. And to accelerate 1 kilogram to 90% of the speed of light requires about 1.2 times 10 to the 17th joules. That is about the same as the energy contained in 2.8 million kilograms of gasoline. Notice how the energy requirements grow much faster than the increase in speed. When you go from 10% to 50% of the speed of light, the speed increases by a factor of 5. But the required energy increases by about 29 times. When you go from 50% to 90% of the speed of light, the speed increases by only 1.8 times. Yet the energy demand rises by roughly 9 times. This is the combined effect of the rocket equation and relativistic physics. And the situation becomes even more difficult because these calculations assume 100% efficiency, meaning all the fuel energy is perfectly converted into motion. In reality, no propulsion system is that efficient. Chemical rockets convert only about 3 to 4% of their energy into useful thrust. Ion engines perform better, reaching roughly 50 to 70% efficiency. Nuclear fusion propulsion, if we ever manage to build it, might achieve around 70 to 80% efficiency. Matter-antimatter annihilation could theoretically reach close to 90% efficiency if nearly all the released energy could be captured and directed for propulsion. But even with perfect efficiency, the energy requirements remain staggering. For example, a spacecraft with a mass of about 1,000 kilograms, roughly the mass of a small car, would require around 1.3 times 10 to the 19th joules of energy to reach 50% of the speed of light. That's about the energy output of a large nuclear power plant running for an entire year. All of that energy would need to be stored on the spacecraft or generated somehow during the journey. If you're using fusion, you'd need to carry fusion fuel. Hydrogen is the lightest fuel, but you'd need tons of it. And remember, the more fuel you carry, the more mass you have, which means you need even more fuel to accelerate that additional mass. The rocket equation is brutal. Every kilogram of payload requires multiple kilograms of fuel. Every kilogram of fuel is additional mass that also needs to be accelerated. This is why conventional rockets can't get us to high fractions of the speed of light. The fuel requirements grow exponentially. By the time you've added enough fuel to reach high speeds, your spacecraft is mostly fuel tanks, and you've reached a point of diminishing returns. This is why ideas like laser sails are attractive. If you don't have to carry your fuel, if the energy comes from an external source like a laser beam from Earth, then you avoid the rocket equation problem. But laser sails have their own issues. The laser needs to be incredibly powerful and precisely aimed. The sail needs to be enormous and incredibly lightweight. And once you've accelerated, you can't slow down unless you have a second laser at your destination, which you don't. So laser sails are great for flyby missions where you're just passing through a star system taking pictures, but not for missions where you want to stop and explore. What about even more exotic propulsion concepts? One famous idea is called the Bussard ramjet, proposed by physicist Robert Bussard in 1960. The concept is surprisingly elegant. As a spacecraft travels through interstellar space, it would collect hydrogen atoms from the interstellar medium using an enormous magnetic scoop. These hydrogen atoms would then be funneled into a fusion reactor on board the spacecraft. The fusion reactions would release energy that could be used to propel the ship forward. In other words, the spacecraft would be refueling as it travels, gathering fuel directly from space itself. This approach would solve one of the biggest challenges of interstellar travel, which is carrying enough fuel for a long journey. In theory, a Bussard ramjet could continue accelerating for a very long time, potentially reaching speeds close to the speed of light. The problem is that the interstellar medium is incredibly sparse. There's only about 1 hydrogen atom per cubic cm in the space between stars. To collect enough hydrogen to fuel a fusion reactor, your magnetic scoop would need to be enormous. Calculations suggest it would need to be thousands of miles across. Building such a structure is beyond anything we can imagine with current technology. And there's another problem. At high speeds, the hydrogen atoms you're scooping up would be hitting you from the front at relativistic speeds. Each atom would act like a tiny particle of radiation. Collectively, they'd create a huge drag force, slowing you down. Some calculations suggest that the drag might actually be greater than the thrust you get from the fusion reactor. If that is correct, then the Bussard ramjet might not work at all. Instead of accelerating the spacecraft, the drag created by collecting particles from the interstellar medium could actually slow it down. That means the Bussard ramjet may be another elegant idea that looks promising in theory, but becomes far more difficult when examined in practice. What about warp drives? This is where the discussion enters truly speculative territory. In 1994, physicist Miguel Alcubierre proposed a theoretical concept that might allow faster-than-light travel without technically violating the laws of relativity. The idea is based on an important principle in physics. Nothing can move through space faster than light. But space itself can expand or contract at any speed. In fact, during the earliest moments after the Big Bang, space expanded far faster than the speed of light. This event is known as cosmic inflation, and it is a well-established part of modern cosmology. So, Miguel Alcubierre proposed that a spacecraft could travel by creating a bubble of space-time around it. Behind the spacecraft, space would expand, effectively pushing the bubble forward. In front of the spacecraft, space would contract, pulling the bubble in the same direction. The spacecraft itself would not actually move through space in the usual sense. Instead, it would remain stationary inside this space-time bubble while the bubble itself moves through space. Since the ship isn't moving relative to the space immediately around it, it wouldn't violate relativity. But the bubble could move faster than light because space can expand and contract faster than light. It's brilliant. It's elegant, and it probably doesn't work. The first problem is that creating this bubble would require exotic matter with negative mass and negative energy density. We have never observed anything with negative mass. Some quantum phenomena can produce extremely small amounts of negative energy density, such as the Casimir effect. But the amounts are unbelievably tiny and nowhere near what would be required to create a warp bubble. At the moment, we have no idea how to produce the kind of exotic matter that such a system would require, especially in the enormous quantities needed. The second major problem is the energy requirement, which would be absolutely enormous. Early calculations suggested you'd need the mass-energy equivalent of the entire observable universe to create a warp bubble big enough for a small spacecraft. Later refinements brought that down to the mass energy of Jupiter, which is still impossible, but at least not as ridiculous. More recent work has brought it down further. But we're still talking about energy levels far beyond anything we can generate. The third problem is that you'd have no way to steer the bubble once you're inside it. The front of the bubble is moving faster than light, so you can't send signals to it from inside the bubble. You'd have to set your course before activating the warp drive and hope you've aimed correctly. The fourth problem is that as you travel, you'd accumulate particles and radiation on the front of your warp bubble. When you deactivate the bubble, all that accumulated energy would be released in a massive burst that would likely destroy your destination. So, warp drives remain firmly in the realm of science fiction. They're not impossible according to our current understanding of physics, but they require technology and energy sources that might as well be magic. What about wormholes in general relativity? It's theoretically possible for space-time to be connected in strange ways. You could have a shortcut through space-time, a wormhole that connects two distant points. Travel through the wormhole, and you could cross vast distances instantaneously, or nearly so. Einstein and Nathan Rosen first proposed this in 1935. Einstein-Rosen bridges, as they're sometimes called, are solutions to Einstein's field equations. They're mathematically valid, but there are problems. First, naturally occurring wormholes, if they exist, would be microscopic. Far too small for anything macroscopic like a spacecraft to pass through. To create a traversable wormhole, one that is large enough and stable enough for an object to pass through, you would need exotic matter. More specifically, you would need matter with negative energy density to keep the wormhole open. Without that, the wormhole would collapse instantly the moment anything tried to pass through it. The second challenge is even more practical. Even if you could create a wormhole, you would still need to move one end of it to your destination. For example, if you wanted a wormhole connecting Earth and Proxima Centauri, one end of the wormhole would have to be transported all the way to that star system first. And that means making the journey using conventional travel at less than the speed of light. Before the wormhole connection could even exist, once it's there, you'd have a shortcut. But creating the shortcut would take just as long as conventional travel. So wormholes don't really help with the initial exploration of space. They might be useful for maintaining connections between already established colonies, but they don't solve the problem of getting there in the first place. Let's come back to more realistic ideas. What if we embraced the slowness? What if we accepted that interstellar travel will take thousands or millions of years and designed our missions accordingly? This brings us to the concept of generation ships. A generation ship is a spacecraft designed to support multiple generations of humans over centuries or millennia. The idea is that the original crew who leave Earth won't live to see the destination. Neither will their children or their grandchildren. Multiple generations will be born, live their entire lives, and die on the ship. Eventually, after many generations, their descendants will arrive at the destination. This concept raises all sorts of questions. How do you maintain a closed ecosystem for thousands of years? Plants produce oxygen and food, but they need water, nutrients, and light. You'd need to recycle everything perfectly. Every drop of water, every nutrient, every atom of carbon would need to be recovered and reused. We've done this on a small scale on the International Space Station, but never for long periods with complete recycling. Losses are inevitable. Some atoms will get incorporated into structures and not be recoverable. Some will leak out through airlocks. Over centuries, these small losses add up. You would need enormous redundancy and large reserves to compensate for failures over such a long journey. Another major challenge is maintaining genetic diversity within a small population. A generation ship might carry a crew of only hundreds or perhaps a few thousand people, which creates a very limited gene pool. Over many generations, this could lead to inbreeding, genetic drift, and the gradual accumulation of harmful mutations. This is a well-known problem in biology. We see similar effects in endangered species, where populations that fall below a certain size begin to suffer from serious genetic issues. To avoid this, a generation ship would need strict population management, possibly including stored genetic material, controlled reproduction, or even advanced genetic engineering to maintain diversity. And beyond the biological challenges lies a social one. How do you maintain social cohesion on a spacecraft where everyone knows they are traveling toward a destination they themselves will never see? They're living their entire lives in a confined space for the benefit of future generations. What keeps them motivated? What prevents social breakdown, conflict, or even mutiny? You'd need strong cultural traditions, a sense of purpose, maybe even religious or philosophical frameworks to give meaning to the journey. And you'd need to preserve knowledge and skills across generations. The people who arrive at the destination need to know how to build a colony, how to survive on a new world. They can't just be passengers. They need to be engineers, scientists, farmers, builders. How do you prevent technological failure? Machines break down, components wear out. Over centuries, every system on the ship will fail multiple times. You'd need spare parts, manufacturing facilities, repair expertise. You'd need to train each generation in the skills needed to maintain the ship. If a critical system fails and there's no one who knows how to fix it, the mission is over. All of these challenges are solvable in principle, but they're difficult, and we've never tested any of this. We've never had a closed ecosystem that's been completely self-sufficient for more than a few years. We've never had a small population isolated for multiple generations. We don't know if it would work. We don't know what problems would arise that we haven't thought of. But let us assume for a moment that we solve all of these problems. Imagine that we successfully build a generation ship that can sustain life for centuries. The next question is simple. How long would it take to travel 1 light year on such a ship? The answer depends entirely on the speed of the spacecraft. If advanced propulsion systems, such as nuclear pulse propulsion or fusion drives, could push the ship to about 5 to 10% of the speed of light, then traveling 1 light year at 5% of the speed of light would take roughly 20 years. That is actually less than a single human generation. So technically, it would not even be a true generation ship. A more realistic estimate might be around 1% of the speed of light, which could be achievable with advanced nuclear electric propulsion. At that speed, traveling 1 light year would take about 100 years. That means the journey would span roughly 3 to 4 generations, depending on how a generation is defined. In that scenario, the great-grandchildren of the original crew would be the ones who finally arrive at the destination at about 0.1% of the speed of light, which might be achievable with very advanced ion propulsion. Traveling a distance of 1 light year would take roughly 1,000 years. That means the journey would span about 30 to 40 generations. By the time the ship arrived, nobody on board would have any living connection to the people who originally left Earth. The departure would exist only as ancient history, preserved through records and stories. At an even slower speed of 0.01% of the speed of light, the journey would take about 10,000 years to travel just 1 light year. That corresponds to roughly 300 to 400 generations. Over such a timescale, entire civilizations on Earth have risen and fallen. The crew that finally arrived at the destination would be so distant from the original crew that they might barely remember the true purpose of the mission. The journey itself could turn into mythology. A story about a distant beginning when their ancestors once departed from a world called Earth. This leads to a deeper philosophical question. If a generation ship travels for 10,000 years, is it still truly the same mission? The people who finally arrive would have no direct connection to the people who originally left Earth. Their entire civilization would have developed and existed on the ship itself. In what sense are they still carrying out a mission planned by people who lived 300 generations before them? They might not even want to colonize another planet anymore. After thousands of years, they could have completely adapted to life aboard the spacecraft. A stable society might have formed in space, with its own culture, Tavan traditions, and identity. To them, the idea of living on a planetary surface might actually seem strange or unnatural. In that case, the original purpose of the journey could slowly fade or transform over time. One of the strange consequences of extremely long generation ship voyages is that the mission itself might evolve, or even be abandoned, by people whose values and desires are very different from those of the original planners. Now let's think about time dilation again. One of the strange effects of special relativity is that time passes differently for objects moving at different speeds. If you're traveling at a significant fraction of the speed of light, time passes more slowly for you than for people who are stationary. This is time dilation, and it's been confirmed experimentally many times. We've sent atomic clocks on fast-moving airplanes and measured that they tick slightly slower than identical clocks on the ground. GPS satellites have to account for time dilation because they're moving fast relative to Earth's surface, at everyday speeds. The effect is tiny. But when speeds approach the speed of light, an effect known as time dilation becomes very important. At 50% of the speed of light, time for the traveler passes at about 87% of the rate experienced by someone who remains stationary on Earth. That means a journey lasting 10 years from Earth's perspective would feel like about 8.7 years for the traveler. At 90% of the speed of light, time slows even more. It would pass at only about 44% of the normal rate. A journey that lasts 10 years on Earth would feel like only 4.4 years for the person on board the spacecraft. At 99% of the speed of light. Time flows at roughly 14% of the normal rate. In that case, a 10-year journey measured on Earth would feel like only about 1.4 years for the traveler. At 99.9% of the speed of light, time would pass at about 4.5% of the normal rate. A 10-year journey from Earth's perspective would feel like roughly 5.4 months on board the spacecraft. So if it was somehow possible to travel at 99.9% of the speed of light, then crossing a distance of 1 light-year would take about 1 year according to observers on Earth. But only about 16 days from the traveler's own perspective. You would age only about 16 days. While everyone on Earth would age 1 full year, if you traveled to Proxima Centauri and then returned to Earth, a journey that would take about 8.5 years from Earth's perspective, you would experience only about 136 days, which is less than 5 months. But everyone you knew on Earth would be 8.5 years older when you came back. If you traveled to a star located 100 light-years away and then returned, the round trip would mean that about 200 years had passed on Earth. But you might only age a few years. You'd return to an Earth where everyone you knew was long dead, where the world had changed beyond recognition. This is the twin paradox, one of the famous thought experiments in special relativity. If you have identical twins, and one stays on Earth while the other travels at near light speed to a distant star and back, the traveling twin will be younger when they reunite. It's not just an illusion. Time really does pass more slowly for the traveling twin. They really do age less. So time dilation offers a way for individual travelers to make long journeys without personally experiencing the full duration. But it doesn't help with the energy problem. You still need enormous energy to accelerate to 99% the speed of light. And it doesn't help the people left behind. While you're zipping across the galaxy, aging a few years, centuries are passing on Earth. If you ever wanted to return home, you'd be returning to a world that had moved on without you. Everyone you knew would be dead. Your entire society might have changed or collapsed. You'd be a time traveler into the future, unable to go back. This has profound implications for any realistic interstellar travel. Even if we develop the technology to travel at high fractions of the speed of light, even if time dilation makes the journey short from the traveler's perspective, the journey is still impossibly long from the perspective of human civilization. Send a ship to a star 100 light-years away, and 100 years will pass before anyone on Earth even knows if it arrived. Another 100 red years would pass before any information came back. That's 200 years total. 8 to 10 generations. Nobody alive when the ship returns will remember the people who left. This makes it very difficult to maintain continuity across interstellar distances. You can't have a unified human civilization spanning many star systems if it takes centuries for information to travel between them. Each colony would be effectively independent, isolated by the vast distances and the finite speed of light. Over time, colonies would diverge. They develop their own cultures, their own languages, maybe even their own subspecies as they adapted to different environments. A colony on a high-gravity planet might evolve to be shorter and more robust. A colony in low gravity might become taller and more fragile. Given enough time, thousands or millions of years, colonies might diverge so much they wouldn't even be the same species anymore. This is speculative. Of course, we don't know how fast human evolution would proceed in different environments, especially if we're using genetic engineering or other technologies. But the point is that interstellar colonization, even if successful, wouldn't create a unified human empire like in science fiction. It would create isolated pockets of humanity, each developing independently, connected only by faint signals taking decades or centuries to travel between stars. Now let us think about the practical economics of interstellar travel. Even if humanity could build a spacecraft capable of reaching another star, an important question remains: who would pay for it? The cost would be enormous. Constructing a fusion-powered generation ship capable of carrying thousands of people could require trillions of dollars, and possibly even tens or hundreds of trillions. Such a project would likely take decades of construction, along with massive industrial infrastructure in space and the commitment of huge amounts of resources. And then there is the question of return on investment. If a colony ship was sent to another star system and the journey took thousands of years, the people who funded the mission would never see any benefit during their lifetimes. Neither will your children or grandchildren. The colony might eventually send back information, but it will take hundreds or thousands of years to receive it. There's no trade possible across interstellar distances. You can't ship goods between stars because the journey takes too long. By the time your cargo arrives, it's obsolete. Information can travel at the speed of light, which is faster than any spacecraft we could build. But even light takes years or decades to cross the vast distances between stars. For example, a colony located 100 light-years away would create enormous communication delays. A single exchange of messages would take about 200 years. You send a message, and 100 years later they receive it. They send a reply, and another 100 years later the response finally reaches you. That is not really a conversation. It is more like leaving messages for people in the distant future. Because of this, there is no clear economic incentive for colonizing other star systems. There are no resources that could realistically be brought back to Earth, no practical trade routes that could be established, and no immediate strategic advantage. The real motivations would likely be exploration, scientific curiosity, and perhaps the most important reason of all, the long-term survival of humanity. These are noble goals, but they don't generate profit. They don't have immediate benefits. In our current economic system, it's hard to justify spending trillions of dollars on a project that won't produce results for thousands of years. Governments might fund such projects for prestige or long-term planning, but even government budgets face political pressure to show results within election cycles. This is one reason why we haven't seen more progress toward interstellar travel. It's not just that it's technically difficult, it's that it's economically irrational from a short-term perspective. The benefits are so far in the future that they might as well not exist from the perspective of current decision-makers. Of course, this perspective could change if humanity begins thinking on much longer timescales. If we start planning not just in years, but in centuries, interstellar colonization might begin to look like a worthwhile investment. If our civilization becomes truly spacefaring, with massive industrial infrastructure spread throughout the solar system, the cost of building interstellar spacecraft could become far more manageable. Another possibility involves the development of self-replicating machines capable of building infrastructure autonomously. In such a scenario, the cost of large space projects could drop dramatically. A small robotic probe could be sent to an asteroid, where it would begin mining raw materials and constructing copies of itself. Those machines could then produce even more machines, creating an exponentially growing network of automated builders capable of constructing spacecraft, habitats, or other infrastructure needed for deep space exploration. With that kind of capability, building a generation ship becomes much more feasible. But we're not there yet. We're still struggling to establish a permanent presence on the Moon. We're still decades away from a human mission to Mars. Interstellar travel is not even on the planning horizon for any space agency. It's something we think about, something we study, but not something we're actively preparing to do. And that's probably wise. There are so many challenges to solve just within our own solar system. We need to learn how to live in space for extended periods. We need to figure out closed-loop life support systems. We need to develop better propulsion systems. We need to build infrastructure for mining and manufacturing in space. All of this is necessary before we can even think about sending humans to other stars. So when you ask how long it would take to travel 1 light-year, the technical answer depends on the technology. With current technology, over 1,000 years; with near-future technology, maybe decades to centuries; with far-future technology, maybe years. But the real answer is that we're not traveling 1 light-year anytime soon. Not because we can't in principle, but because we haven't solved all the prerequisite problems. We haven't built the infrastructure. We haven't developed the technology. We haven't committed the resources. And maybe we never will. Maybe interstellar travel will remain forever beyond our reach. Not because it's physically impossible, but because it's impractical. Maybe humanity's future is in this solar system. Building habitats, terraforming moons, creating a civilization that spans the planets but never leaves the sun's gravitational embrace. There's nothing wrong with that. The solar system is vast. There's room for trillions of people. If we build habitats in space, there are resources enough to support a civilization for millions of years. We could have a rich, diverse, thriving civilization without ever leaving the solar system. Or maybe thousands of years from now, we'll look back at this era and laugh at how limited our thinking was. Maybe we'll have technologies we can't even imagine today. Maybe we'll have solved the energy problem, the propulsion problem, the life support problem. Maybe we'll have colonies around hundreds of stars. Maybe humanity will spread across the galaxy over millions of years, slowly but steadily, expanding our reach. But that's speculation. That's hope for a distant future. For now, 10 for us. 1 light-year remains an impossible distance. Let me give you one more way to think about this. Imagine you could convert matter directly into energy with 100% efficiency. This is what happens in matter-antimatter annihilation. Every kilogram of matter contains a tremendous amount of energy according to Einstein's equation, written as energy equals mass times the speed of light squared. If 1 kilogram of matter were converted completely into energy, it would release about 9 times 10 to the 16 joules of energy. That is roughly equivalent to the energy contained in 21.5 megatons of TNT, comparable to the yield of the largest nuclear weapons ever tested. Now imagine you want to accelerate a spacecraft to 50% of the speed of light, and then slow it down again when it reaches its destination. You would need energy not only to speed up, but also to decelerate at the end of the journey. For a spacecraft carrying a payload of about 1,000 kilograms, the total energy required would be roughly 2.6 times 10 to the 19 joules. If this energy came from matter-antimatter annihilation with perfect efficiency, the spacecraft would need about 290 kilograms of fuel, consisting of 145 kilograms of normal matter and 145 kilograms of antimatter. At first glance, that does not sound like very much. A few hundred kilograms of fuel seems manageable. But the real problem is not the amount. The real problem is that we cannot produce antimatter in meaningful quantities. The total amount of antimatter ever produced by humanity is less than 20 nanograms, which means less than 20 billionths of a gram. To produce 145 kilograms of antimatter at the current rate would take about 300 trillion years. That is roughly 22,000 times the age of the universe. So, even if perfect energy conversion were possible, we would still be limited by our inability to produce and store antimatter. And this already assumes 100% efficiency in converting energy into thrust, which is impossible in the real world. Actual engines always lose energy through heat, radiation, and other inefficiencies in the conversion process. You'd probably need several times more fuel to account for these losses. The point is that even in the most optimistic scenarios with technologies that are theoretically possible but practically impossible, traveling 1 light-year is still enormously difficult. It requires energy levels and technologies far beyond what we have today. And 1 light-year is only the beginning. The nearest star system is about 4¼ light-years away. Most stars in our galaxy are located dozens, hundreds, or even thousands of light-years away. The Milky Way galaxy itself is about 100,000 light-years across. The nearest large galaxy, Andromeda, lies roughly 2 million light-years away. And when we look at the largest scale we can observe, the observable universe spans about 93 billion light-years across. 1 light-year is tiny on cosmic scales. It's the smallest unit of interstellar distance, and yet it's vast beyond our ability to cross with any technology we can currently imagine building. This is the fundamental reality of living in this universe. The speed of light is finite. Distances are vast. Energy is limited. We are slow and small and bound to this corner of space by physics itself. You can rail against it. You can dream of warp drives and wormholes and ways to cheat the laws of physics. But until someone discovers new physics, until someone finds a loophole in relativity that we haven't seen in over 100 years of testing, we're stuck with these limitations. The stars are beautiful. They're fascinating. They're full of wonders we'd love to explore. But they're far away. So far away that 1 light-year, the smallest step toward them, might as well be infinite. And yet knowing this, understanding our limitations, there's still something wonderful about looking up at the night sky. Because even though we can't reach the stars, we can see them. We can study them. We can learn about them. We can understand how they work, what they're made of, how they live and die. We can discover planets around other stars. We can search for signs of life. We can wonder if somewhere out there around some distant star, someone else is looking up at their night sky and wondering the same things we are. The distance might separate us forever. But the questions, the curiosity, the wonder, those are universal. And maybe that's enough. Maybe the journey isn't about physically reaching other stars. Maybe it's about expanding our understanding, pushing the boundaries of knowledge, learning everything we can about this vast universe we find ourselves in. We might never leave this solar system, but our knowledge, our understanding, our curiosity can reach across light years. Our telescopes can see galaxies billions of light years away. Our mathematics can describe the birth of the universe and the death of stars. Our minds can grasp concepts that span time and space in ways our bodies never will. And in that sense, we've already traveled farther than any spacecraft ever could. We've already crossed distances that would take light billions of years to traverse. We've already explored the universe in the only way that really matters, through understanding. So when someone asks how long it would take to travel 1 light-year, the answer is complex. Physically, with current technology, over 1,000 years. With future technology, maybe decades or centuries. With impossible technology, maybe years or months. But intellectually, we've already made that journey. We've already crossed that distance in our minds, in our mathematics, in our understanding of the cosmos. And that journey, the journey of discovery and understanding, never ends. There's always more to learn, always more to discover, always more questions to ask. The physical journey to the stars might be impossible, but the intellectual journey has no limits, and in the end, maybe that's the journey that matters most. Let us look at some historical attempts to seriously think about interstellar travel. Because humanity has been dreaming about reaching the stars for far longer than many people realize. In 1973, the British Interplanetary Society launched a research study called Project Daedalus. The goal was to design an unmanned interstellar probe capable of reaching Barnard's star. a star located about 6 light-years away, within a human lifetime. The design they proposed was extremely ambitious. The spacecraft would be powered by a 2-stage nuclear fusion rocket. The first stage would operate for about 2.05 years, accelerating the spacecraft to roughly 7.1% of the speed of light, after which that stage would be discarded. The second stage would then ignite and continue accelerating the spacecraft even further. The second stage would continue burning for about 1.76 years, bringing the final velocity to roughly 12% of the speed of light. At that speed, the journey to Barnard's star would take about 50 years. When you include the time required for acceleration, the total mission duration would be around 54 years. The people who launched the spacecraft might still be alive when it arrived, although they would likely be quite old. The Project Daedalus design was enormous. At launch, the spacecraft would have a total mass of about 54,000 tons. Most of that mass would be fuel. Around 50,000 tons of deuterium and helium-3 would be needed to power the fusion reactors. The actual payload, meaning the scientific instruments, would weigh only about 500 tons, which is less than 1% of the total spacecraft mass. This is a clear illustration of the tyranny of the rocket equation, where most of a spacecraft's mass must be dedicated to fuel rather than the payload itself. To carry 500 tons of scientific instruments, the spacecraft would need about 50,000 tons of fuel, a ratio of roughly 100 to 1, and that is using nuclear fusion, one of the most efficient propulsion methods scientists can realistically imagine. Project Daedalus was never actually built. It remained a detailed design study, an exploration of what might be possible with advanced technology. But it was not a casual idea. The British Interplanetary Society spent years carefully developing the concept and analyzing whether such a mission could work. They calculated trajectories, designed engines, figured out how to manufacture helium-3, which doesn't exist naturally on Earth in any significant quantity. You'd have to mine it from the atmospheres of gas giant planets or the surface of the Moon. The conclusion was that Project Daedalus was theoretically possible. Nothing in the design violated known physics, but it would require an enormous commitment of resources and decades of technological development. We'd need to master fusion propulsion. We'd need infrastructure in the outer solar system to mine helium-3. We'd need the ability to build massive structures in space. None of this exists today, and we're not close to having it. During the 1980s and 1990s, another concept called Project Longshot was proposed. This was also a detailed design study for an interstellar probe. Longshot was intended to travel to Alpha Centauri, the nearest star system, located about 4.37 light-years away. The spacecraft would use a fusion rocket burning deuterium and helium-3, similar to the propulsion system proposed for Project Daedalus. However, the Longshot design was smaller and slower. The spacecraft would reach a speed of about 4.5% of the speed of light, and the journey to Alpha Centauri would take roughly 100 years. Like Daedalus, the concept was considered feasible in principle, but far beyond the technological capabilities we have today. In the 21st century, new proposals have continued to explore interstellar travel. One of these is Project Icarus, which began in 2009 as a modern redesign of Project Daedalus, updated using current scientific knowledge and improved engineering concepts. The goal was the same as earlier studies: design an unmanned interstellar probe capable of reaching a nearby star within about 1 century. Project Icarus incorporated improvements in materials, propulsion concepts, and scientific instruments that were not available in the 1970s. The result was a design similar in spirit to Project Daedalus, but more efficient. Even so, the spacecraft would still be enormous, still require fusion propulsion, and still remain far beyond what humanity can actually build today. Then there is Breakthrough Starshot, which is very different from the earlier studies because it is being actively explored with real funding and ongoing research. The project was announced in 2016, funded by billionaire Yuri Milner and supported by physicist Stephen Hawking before his death. The idea is to send thousands of extremely small spacecraft, each weighing about 1 gram, toward Alpha Centauri. Each probe would carry a light sail a few meters across. A powerful ground-based laser array on Earth would shine on these sails, accelerating the tiny spacecraft to about 20% of the speed of light within just a few minutes. At that speed, the journey to Alpha Centauri would take about 20 years. Add another 4 years for the data to come back at light speed, and you're looking at about 24 years from launch to receiving data. This is exciting because it's actually achievable with technology that's close to what we have now. The challenges are significant, but not insurmountable. The lasers required for this concept would need to be extremely powerful. But humanity is already developing increasingly powerful lasers for a variety of scientific and industrial purposes. The sails must be ultra-lightweight and highly reflective. And researchers are currently exploring advanced materials that might make this possible. The spacecraft themselves would also need to be extremely miniaturized. But modern electronics are becoming smaller and more efficient every year. The greatest challenge may actually be precision aiming. When a tiny spacecraft is being accelerated to 20% of the speed of light using a laser beam, the beam must remain perfectly focused on the sail during the entire acceleration period. As the spacecraft moves faster and faster, the laser system must continuously track its motion with extraordinary accuracy. Even a very small error in aiming could cause the spacecraft to drift off course, or the beam to miss the sail completely. But these challenges are primarily engineering problems, not fundamental barriers in physics. Researchers are actively working on possible solutions if Breakthrough Starshot were to succeed. It could become humanity's first true interstellar mission. A tiny probe weighing about 1 gram could travel across 4.37 light-years and reach the Alpha Centauri system in roughly 20 years. During its brief flyby, it could transmit images of the star system, possibly capture close-up pictures of nearby planets, and send back data about the system's composition and physical properties. And all of this could happen within the lifetime of the people who launched the mission, which makes the idea incredibly exciting. It would represent a genuine step toward interstellar exploration, even if it is only a small first step. However, it is important to notice what Breakthrough Starshot cannot do. It cannot send humans. It cannot slow down once it reaches its destination. And it cannot carry large or complex scientific instruments. It would be a flyby mission, racing past its target at about 20% of the speed of light, capturing images for only a few minutes before continuing onward into the darkness of interstellar space. That is still far better than nothing. But it is not the kind of exploration that science fiction has taught us to imagine. We are not sending astronauts to land on an exoplanet and study it up close. Instead, we would be sending a camera roughly the size of a microchip, rushing past the system at about 60 million miles per hour, hoping to capture a few valuable images before the probe disappears into deep space forever. This is the reality of interstellar exploration with anything close to current technology. Small probes on fast flyby missions. No humans. No sample return. No long-term study, just a quick glimpse as we race past at a fraction of light speed. And even this requires decades of development and billions of dollars in funding. Now let us think more deeply about the human side of interstellar travel. Imagine that humanity eventually builds a generation ship. Suppose we solve all the technical challenges and send a crew of 1,000 people toward a star located 10 light-years away. If the spacecraft traveled at about 1% of the speed of light, the journey would take roughly 1,000 years. That would span about 30 generations of people living and dying aboard the same ship. What would life actually be like on such a vessel? For the first generation, the people who volunteered for the mission, there would likely be a strong sense of excitement. They would see themselves as pioneers, the founders of a new chapter in human history, setting out on a journey that no one had ever attempted before. They're pioneers, explorers, part of humanity's greatest adventure. They're leaving Earth behind to ensure humanity's future among the stars. There's purpose and meaning in that. But they know they'll never see the destination. They'll spend their entire lives on the ship, working to keep it running, raising children who will continue the mission. The second generation born on the ship never chose this. They were born into the mission. Earth is a story their parents tell them, a place they've never seen and never will. The ship is their entire world. By the third or fourth generation, Earth is ancient history. It's a mythical place, the cradle of humanity, but not home. Home is the ship. By the 10th generation, Earth might seem as distant and unreal as Atlantis does to us. A story, possibly true, possibly embellished over the centuries. By the 20th generation, the mission itself might have changed. The descendants might not care about reaching the destination. They've built a life on the ship. They have a functioning society, culture, history. Why give that up to land on some unknown planet by the 30th generation when the ship finally arrives? Who knows what the people on board will decide to do? Maybe they'll be excited to finally fulfill the mission their ancestors started. Maybe they'll be indifferent or even resentful. Over time, the purpose of the journey could slowly fade. After many generations, people might even forget why their ancestors began traveling in the first place. This is one of the great unknowns surrounding generation ships. We simply do not know how human societies would evolve in such isolation over such vast stretches of time. It is possible that the original mission might not survive unchanged across many generations. Another major concern is the preservation of knowledge. The people who eventually arrive at the destination would need a wide range of skills and understanding. They would need knowledge of agriculture, engineering, biology, physics, medicine, and many other fields. Both practical abilities and deep scientific knowledge would be essential if they were expected to build a functioning civilization on a new world. The question is how to ensure that this knowledge is preserved accurately over 30 generations. If even one generation fails to properly learn or transmit something essential, that knowledge could disappear permanently. And once it is lost, it might never be recovered. You'd need extensive libraries, educational systems, maybe even AI tutors to ensure knowledge continuity. But even then, there's no guarantee. Societies change. Priorities shift. What seems important to one generation might be ignored by the next. And if critical knowledge is lost, the mission could fail even after successfully reaching the destination. Imagine arriving at a new world after a 1,000-year journey, only to realize that nobody remembers how to build the equipment needed to establish a colony. The knowledge was in the ship's databases, but nobody bothered to learn it because they'd lived their entire lives in space and saw no need for planetary survival skills. This is not a far-fetched scenario. The great we've seen knowledge lost on Earth over much shorter timescales. The Romans knew how to make concrete that could last millennia, a technique we only rediscovered in modern times. The ancient Greeks built intricate mechanical computers like the antimatter mechanism, knowledge that was lost for centuries. If knowledge can be lost on a planet with millions of people and extensive records, how much more vulnerable is it on a ship with 1,000 people? These are the kinds of problems that make generation ships so challenging. It's not just about building the ship and keeping it running. In the end, the challenge is not only about building a spacecraft, It is about maintaining a stable, functioning, knowledge-preserving society over timescales longer than most civilizations on Earth have ever lasted. Now let us shift perspective and think about this from the standpoint of physics and the nature of the universe itself. Why is the speed of light what it is? Why is it about 186,000 miles per second? And not faster or slower? The answer is that the speed of light is built into the very structure of space-time. It is not just a property of light itself, but a fundamental limit woven into the fabric of the universe. It's not just the speed that light happens to travel. It's the maximum speed at which any information can propagate through space. It's the speed of causality itself. In special relativity, the speed of light is the conversion factor between space and time. It's what makes space-time a unified four-dimensional structure rather than separate three-dimensional space and one-dimensional time. The fact that the speed of light is finite and has the value it does is fundamental to how the universe works. If the speed of light were infinite, the universe would behave very differently. Cause and effect would happen simultaneously across any distance. There would be no light, travel time, and no delay between events happening in different parts of space. If the speed of light were much slower, for example, 1,000 miles per second, instead of about 186,000 miles per second, interstellar travel would become even more impossible. Light itself would need tens of thousands of years to cross a distance of 1 light year, assuming we would still use that term. And if the speed of light were faster, perhaps 1 million miles per second, the universe would feel smaller in a certain sense because light would cross distances more quickly. Time dilation would still occur at high speeds, but it would begin only at much higher velocities. Even then, the fundamental limit would still exist. No matter what the value might be, nothing could exceed the speed of light. Whatever that limit happened to be, it would still remain the ultimate speed boundary of the universe. The reality is that we are living in the universe we have. The speed of light has the value it does because it emerges from the fundamental constants of physics, including the strength of electromagnetic interactions and the properties of empty space itself. Specifically, the permeability of free space and the permittivity of free space. These constants determine the speed of light. Change those constants and you'd change the universe in fundamental ways. You might not even have atoms or stars or planets. So we can't wish for a faster speed of light. We have to work within the constraints of the universe we inhabit. And in this universe, 1 light year is a vast distance that takes light 1 year to cross. For anything moving slower than light, which is everything with mass, it takes longer, much longer. If you're using technology anywhere close to what we have now, there's something philosophically profound about this. The universe has built-in limitations. There are places we can see but can never reach, even in principle. There are events happening right now in distant galaxies that we won't see for millions or billions of years. By the time the light from those events reaches us, the events themselves are ancient history. The stars we see in the night sky, we're seeing them as they were years or centuries or millennia ago, not as they are now. Betelgeuse, which I mentioned earlier, is about 550 light years away. The light we see from Betelgeuse tonight actually left that star around the year 1474. If Betelgeuse had exploded as a supernova last week, we would not know about it for another 550 years. Information can travel only at the speed of light. And the speed of light is finite. Because of this limit, the universe has something like a cosmic horizon. There are events happening right now in distant regions of space that we simply cannot see yet, because their light has not had enough time to reach us. Not just in space, but in time. There are events happening beyond our cosmic horizon that we will never know about because the light from them will never reach us. The universe is expanding and the expansion is accelerating. Distant galaxies are moving away from us faster than the speed of light because space itself is expanding between us and them. Light from those galaxies will never reach us. We can never know what happens there. We can never travel there. Those parts of the universe are fundamentally inaccessible to us now and forever. This is the cosmic horizon, and it's shrinking. As the universe continues to expand and accelerate, more and more galaxies will cross beyond the horizon. Billions of years from now, observers in our galaxy will only be able to see our local group of galaxies. Everything else will have receded beyond the cosmic horizon. The universe will appear smaller, lonelier, unless they have historical records from our era. Future astronomers might not even know that there are billions of other galaxies out there. They'll think the universe is just the local group, a few dozen galaxies in an otherwise empty void. This is humbling. We live in a special time when the universe is still young enough and the expansion hasn't progressed so far that we can still see billions of galaxies. We can still study the cosmic microwave background, the afterglow of the Big Bang. We can still observe the large-scale structure of the universe. Future civilizations, if they exist, won't have that privilege. So in a sense, we should appreciate the view we have now. We can see farther and know more about the universe than any future civilization will be able to. Even if we can never travel to those distant galaxies, we can at least observe them, study them, learn from them. That's something. Now, let's come back to the question of why we care about traveling 1 light year or any interstellar distance. Why does it matter? What's the motivation for wanting to reach other stars? One reason is survival. Earth won't last forever. In about 1 billion years, the sun will have brightened enough that Earth's oceans will evaporate. The planet will become uninhabitable for complex life. In about 5 billion years, the sun will expand into a red giant, possibly engulfing Earth entirely. Even if Earth survives, it will be scorched and lifeless. If humanity wants to survive beyond those timescales, we need to leave the solar system. One reason humanity may eventually explore the stars is the long-term future of our planet. Over extremely long timescales, conditions on Earth will change, and at some point humanity may need to find new homes around other stars. But 1 billion years is an incredibly long time. All of recorded human history covers only about 5,000 years. That means 1 billion years is roughly 200,000 times longer than the entire span of human civilization that we know today. So there is no immediate urgency. Humanity still has an enormous amount of time to develop the technology required for interstellar travel. Another powerful reason is something much more human: curiosity. We want to know what exists beyond our solar system and what kinds of worlds might be waiting among the stars. Are there planets like Earth around other stars? We know there are planets. We've detected thousands of exoplanets using telescopes. But are any of them habitable? Do any of them have life? The only way to know for sure is to go there and look. Telescopes can tell us a lot, but there are limits to what we can learn from light years away. We can analyze the spectra of an exoplanet's atmosphere and look for biosignatures, chemical indicators that life might be present. But we can't be certain without visiting. There could be microbial life that doesn't produce detectable biosignatures. There could be complex life that we miss because we're looking for the wrong signs. The only way to be absolutely sure is to send a probe, or better yet, send humans. But as we've established, sending anything to another star is incredibly difficult. So, we're left with a frustrating situation. We know there are thousands of planets out there. Some of them probably Earth-like. Some of them possibly inhabited. But we can't reach them. We can only look from a distance and wonder. It's like being a child standing outside a candy store, seeing all the sweets inside. But the door is locked and you don't have the key. The candy is there. You can see it, but you can't have it. That's humanity's relationship with the stars. We can see them. We can study them. But we can't reach them. At least not with anything close to current technology. Maybe that will change. Maybe in a few centuries. We'll have fusion drives or antimatter engines or something we haven't thought of yet. Maybe we'll send generation ships to nearby stars, slowly building a network of human colonies across the galaxy. Maybe we'll discover new physics that allows faster than light travel, though that seems very unlikely. Or maybe we'll never leave the solar system. Maybe the distances are just too great and the resources required are too vast. Maybe we'll build a thriving civilization within the solar system. Billions of people living in space habitats and on terraformed moons, but never venturing to the stars. Both futures are possible. We don't know which one we'll get. What we do know is that right now, today, traveling 1 light year is effectively impossible. It would take over 1,000 years with our fastest spacecraft. It would take decades or centuries with optimistic future technology. It would require energy levels and engineering capabilities far beyond what we currently have. 1 light year is a tiny distance on cosmic scales. It's less than the distance to the nearest star. But it's vast by human standards. It's a distance that might as well be infinite given our current limitations. And that's the reality we have to accept. We live in a universe where distances are immense and speeds are limited. We're slow creatures on a small planet looking out at a cosmos we can observe but not traverse. It's humbling. It's frustrating. But it's also beautiful in its own way. The universe is vast and mysterious. There are wonders beyond counting, spread across billions of light years. We'll never see most of them in person, but we can imagine them. We can study them from a distance. We can dream about them. And maybe that's enough. Maybe the journey isn't about reaching the stars physically. Maybe it's about reaching for understanding, pushing the boundaries of knowledge as far as we can, learning everything we can about this incredible universe we find ourselves in. Because even though we cannot travel 1 light year within a human lifetime, we have already explored the universe in ways that truly matter. Humanity has mapped galaxies billions of light years away. We have detected gravitational waves created when black holes collided in the distant past. And we have observed the cosmic microwave background, the faint radiation left over from a time when the universe was only about 380,000 years old. We've discovered thousands of exoplanets and learned that planets are common throughout the galaxy. We've developed a mathematical description of the universe from its first moments to its ultimate fate. We've done all of this without leaving Earth, or at most without going farther than the moon. Our bodies might be confined to this small corner of space, but our minds, our understanding, our knowledge, they've traveled farther than any spacecraft ever could. And in the end, that might be the most important journey of all. Let me give you some more ways to grasp just how impossibly far 1 light year really is. We have talked about time and how long it takes to travel such a distance. But let us think about the scale in a way that might feel more concrete. Imagine driving a car at a steady highway speed of 60 miles per hour, without ever stopping. How long would it take to drive a distance of 1 light year? 1 light year is about 5,878,625,000,000 miles. If you divide that distance by 60 miles per hour, you get roughly 97,977,000,000 hours of driving time. When you convert that into years, the result is about 11,181,000 years of continuous driving. That means you would need to drive for more than 11 million years to cover the distance of 1 light year. Modern humans have existed for only about 300,000 years. So the journey would have had to begin long before our species appeared. You would have needed to start driving when our distant ancestors were still Homo erectus, a completely different human species. There were no cars, no roads, no wheels, and no civilization of any kind. Humans were only beginning to use stone tools and learning how to control fire. And you would still be driving today, with millions of years left to go. That is what the distance of 1 light year looks like if you travel at 60 miles per hour. Now imagine you could walk instead. The average human walking speed is about 3 miles per hour. At that pace, walking a distance of 1 light year would take roughly 222,362,000 years. To understand how long that is, consider that the asteroid that wiped out the dinosaurs struck Earth about 66 million years ago. Walking 1 light year would take more than 3 times longer than the time that has passed since that event. You would have needed to start walking before there were any primates, before mammals larger than a shrew existed, when dinosaurs still dominated the Earth. And even after walking for all that time, you would still be walking today, with more than 150 million years left to go. What if you could run instead? A marathon runner can maintain a pace of about 6 miles per hour for more than 26 miles. Running is faster than walking, but still much slower than driving. At a speed of 6 miles per hour, running a distance of 1 light year would take about 111,181,000 years. That is still longer than the entire age of the dinosaurs on Earth. Now consider the fastest commercial aircraft. A Boeing 747 cruises at about 570 miles per hour. Even at that speed, flying a distance of 1 light year would take roughly 1,176,000 years. Once again, we are dealing with timescales longer than the entire existence of modern humans. Every form of transportation we currently use, from walking to the fastest passenger jets, is incredibly slow compared with the distances between stars. Even our fastest spacecraft, the Parker Solar Probe, which can reach about 430,000 miles per hour, would still require roughly 1,560 years to travel 1 light year. Now think about it another way. Light can circle the Earth along the equator about 7.5 times in a single second. During that same second, how far does our fastest spacecraft travel? The Parker Solar Probe moves about 119 miles in 1 second, while light travels roughly 186,000 miles in that same second. In other words, light moves about 1,560 times faster than our fastest spacecraft. That enormous gap is the challenge humanity faces when we talk about traveling to the stars. We are not even close. We are not within 1 order of magnitude, or even 2. The gap between our fastest spacecraft and the speed of light is still more than 1,500 times, which shows just how immense the challenge really is. Here is another comparison that makes this easier to feel. The distance from Earth to the Moon is about 238,900 miles. Light takes about 1.3 seconds to travel from Earth to the Moon. Radio signals, which also travel at the speed of light, need about 1.3 seconds to get there as well. That is why conversations between astronauts on the Moon and mission control on Earth always include a noticeable delay. By contrast, the Parker Solar Probe would take about 33 minutes to travel the same distance from Earth to the Moon. And when you compare that with 1 light year, the scale becomes overwhelming. 1 light year is about 24,665 billion times farther than the distance between Earth and the Moon. That is a number so large it becomes difficult to truly imagine. If you could line up 24,665 billion Earth-to-Moon distances end to end, you would finally reach a distance of 1 light year. Here is another way to visualize it. The distance from Earth to the Sun is about 93 million miles. Astronomers call this distance 1 astronomical unit, often written as 1 AU. Light takes about 8 minutes and 20 seconds to travel 1 astronomical unit. If the Sun were to suddenly disappear, we would not know immediately. It would take 8 minutes and 20 seconds for that information to reach Earth, because the signal could travel no faster than the speed of light. At its maximum speed, the Parker Solar Probe would take about 9 days to travel that same distance of 1 astronomical unit. But a full light year equals about 63,241 astronomical units. which means it is 63,241 times farther than the distance between Earth and the Sun. Now imagine a scale model. Suppose the distance between Earth and the Sun in this model is just 1 inch. On that scale, a distance of 1 light year would be about 63,241 inches, which is roughly 5,270 feet, or about 1 mile. And on that same scale, the nearest star system, Proxima Centauri, would not be next door. It would be about 4.24 miles away. The center of the Milky Way would lie about 26,000 miles away on that same scale. The Andromeda Galaxy would be about 2.5 million miles away. These scales are extremely difficult for the human mind to grasp. No matter how you look at it, 1 light year is enormous. It is a distance that far exceeds anything we experience in everyday life. And it is far larger than the entire solar system. For example, Neptune, the outermost major planet, orbits the Sun at about 30 astronomical units. 1 light year is about 2,108 times farther than the distance between the Sun and Neptune. If Neptune's orbit were represented as 1 inch in diameter, then 1 light year would be about 175 feet away, roughly the height of a 15-story building. Now imagine what it would actually feel like to travel 1 light year. Suppose you boarded a spacecraft capable of reaching 50% of the speed of light. From the perspective of the ship, the journey would take about 2 years. Although more time would pass on Earth because of time dilation, as the spacecraft accelerated, the stars around you would begin to change appearance. Light from stars behind the ship would become red-shifted as you moved away from them. Light from stars in front of you would become blue-shifted as you moved toward them. This phenomenon is known as the relativistic Doppler effect. As your speed approached half the speed of light, the effect would become dramatic. Stars ahead of you would appear bluer and brighter, while stars behind you would appear redder and dimmer. The entire pattern of stars across the sky would begin to shift and distort as your velocity increased. More stars would appear to be concentrated ahead of you, fewer behind. This is called relativistic beaming or the headlight effect. The faster you go, the more pronounced it becomes. At 90% light speed, almost all the starlight would appear to be coming from a small cone ahead of you. The stars behind and to the sides would appear to dim almost to invisibility. As you traveled, nearby stars would show parallax. Their positions relative to distant background stars would shift as you passed them. At 50% light speed, covering half a light year in 1 year, nearby stars would noticeably change position. Stars that were ahead of you would pass to the side and then behind. Stars that once appeared to the side of your spacecraft would gradually shift toward the region behind you. At the same time, new stars would seem to gather in front of the ship. The constellations would begin to change. Familiar patterns in the night sky would slowly distort and eventually become impossible to recognize. The Big Dipper, Orion, Cassiopeia, and every constellation people on Earth have known for thousands of years would stretch, bend, and transform into completely different shapes as your velocity through space increased. New patterns would emerge, and when you arrived, 1 light year away from where you started, the night sky would be completely different. Earth's sun would be just another star among thousands. Not particularly bright or remarkable. Just one more point of light in the darkness. If you had a powerful enough telescope, you could look back and see the solar system. You could see the planets, tiny dots of reflected light orbiting a yellow star. You could see Earth, a pale blue dot like the famous Voyager photograph, but from a different angle. You might feel the isolation. You'd be farther from home than any human has ever been. Farther than the moon. Farther than Mars. Farther than any planet. You'd be in interstellar space in the vast darkness between stars. The nearest star to you might be several light years away. You'd be utterly alone, surrounded by emptiness with no hope of rescue if something went wrong. This is the reality of interstellar travel. Even if we could travel at high fractions of light speed, even if the journey only took a few years, it would be a profound psychological challenge. The isolation would be absolute. The distance would be incomprehensible. The risk would be enormous. And yet, some people would probably volunteer for it. Throughout history, humans have always been explorers. We've crossed oceans in wooden boats, not knowing what lay on the other side. We've climbed mountains because they were there. We've explored caves, deserts, polar ice caps, the deepest parts of the ocean. We've sent astronauts to the moon, knowing the risks. When given the chance, some humans always choose to explore, to push boundaries, to see what's over the next horizon. If we ever develop the technology to travel to other stars, there will be volunteers. People willing to leave everything behind, knowing they might never return for the chance to see something no human has ever seen. To set foot on a planet orbiting another star, to be the first. That drive, that curiosity, that willingness to risk everything for discovery, that's one of humanity's defining characteristics. It's taken us from small tribes in Africa to a global civilization. It's taken us to the moon and sent our robots to every planet in the solar system. Maybe someday it will take us to the stars. But that day is not today. Today, 1 light year remains an impossible distance. Now, let's talk about what we've accomplished despite these limitations. In the last few decades, we've discovered thousands of exoplanets, planets orbiting stars other than the Sun. Before 1992, we didn't know of a single planet outside our solar system. For a long time, astronomers suspected that planets around other stars must exist, but we had no direct proof. That changed in 1992, when astronomers discovered the first confirmed exoplanets orbiting a pulsar, the dense remains of a dead star. Then, in 1995, scientists made another historic discovery. They found the first planet orbiting a Sun-like star, known as 51 Pegasi b. That moment marked the true beginning of modern exoplanet astronomy. Since then, discoveries have accelerated dramatically. Today we know of more than 5,000 confirmed exoplanets, with thousands more candidates still waiting to be confirmed by future observations. These discoveries have revealed an astonishing diversity of worlds. Astronomers have found hot Jupiters, giant planets orbiting extremely close to their stars and heated to thousands of degrees. We have discovered ice giants similar to Neptune. But orbiting distant stars, there are rocky planets similar in size to Earth, and some that lie within the habitable zone, where liquid water could potentially exist. Scientists have also identified super-Earths, rocky planets larger than Earth but smaller than Neptune, along with a large population of mini-Neptunes. Worlds that fall somewhere between rocky planets and gas giants in size and composition. Planets between Earth and Neptune in size. We found planets orbiting binary stars, something that was thought to be impossible. We found planets orbiting the remnants of dead stars. We found planets that orbit their stars backwards in retrograde orbits. We found planets that are pitch black, absorbing nearly all the light that hits them. We found planets that might rain glass sideways due to their extreme winds. We found planets that might have oceans of liquid lava. We've even found a few planets that might be genuinely Earth-like. Rocky planets about Earth size, orbiting in the habitable zone of Sun-like stars where temperatures might allow liquid water. Planets like Proxima Centauri b orbiting the nearest star to our Sun. Planets in the TRAPPIST-1 system, where 7 Earth-sized planets orbit a small red dwarf star, 3 of them in the habitable zone. Planets around Kepler 442, Kepler 452, and dozens of other stars. We don't know if any of these planets actually have life. We can't see them clearly enough to know. They're too far away and they're too small and dim compared to their stars. But we're working on it. The James Webb Space Telescope, launched in 2021, is analyzing the atmospheres of exoplanets by looking at how starlight filters through a planet's atmosphere during a transit. When the planet passes in front of its star, we can determine what gases are present: oxygen, methane, water vapor, carbon dioxide. All of these leave distinct signatures in the spectrum. If we find oxygen and methane together, that might indicate life on Earth. Oxygen and methane don't coexist naturally. Oxygen reacts with methane and destroys it. The only reason we have both in Earth's atmosphere is because living organisms constantly produce both. Plants produce oxygen. Bacteria and cows and other organisms produce methane. Without life continuously replenishing both gases, they'd react and disappear. So, if we find a planet with both oxygen and methane in its atmosphere, that's a strong hint that something is producing those gases. That something might be life. We haven't found such a planet yet. But we're looking, and the fact that we're analyzing the atmospheres of planets orbiting stars dozens or hundreds of light years away is remarkable. We can't go there. We can't send a probe. We can't travel 1 light year, let alone dozens or hundreds. But we can study those planets from here. We can learn about them. We can search for signs of life. And if we find it, if we discover life on another world, it will be one of the most profound discoveries in human history. Even if we can never go there. Even if we can never meet whatever forms of life might exist. Just knowing that life exists elsewhere would change everything. It would tell us that we're not alone. It would tell us that life is not a cosmic fluke, a one-time accident that happened only on Earth. It would tell us that the universe is teeming with life, that wherever conditions are right, life finds a way. And maybe someday we'll find intelligent life. Maybe we'll detect radio signals from a distant civilization. Maybe we'll see the signatures of technology, heat signatures from megastructures, or unusual spectral lines from industrial pollution. Maybe we'll find evidence that we're not the only species that has built a civilization that has looked up at the stars and wondered. And if we do, what then? We still can't travel to them. If they are 100 light years away, any message we send will take 100 red years to reach them. Their reply will take another 100 red years to come back. A single exchange of messages would take 200 years. Everyone involved in sending the first message would be dead before the reply arrived. But maybe that's okay. Perhaps simply knowing that other worlds exist is already enough. Perhaps the conversation itself, even if it stretches across centuries, would still be meaningful. Even if no single person experiences both sides of it. Humanity could maintain a dialogue with another civilization, exchanging ideas and knowledge across thousands of years. Our great-great-great-grandchildren might receive messages that we once sent. Their own great-great-grandchildren might eventually receive the replies to our answers. It would be a conversation unlike anything in human history. Slow and patient, unfolding across generations, yet still real. This may be the kind of future humanity actually experiences. Not a universe like Star Trek, where ships move between stars in a matter of days or weeks. Not a galaxy like Star Wars, where hyperspace jumps cross enormous distances instantly. Instead, it might be a future where civilizations remain connected through light, radio waves, and information. Traveling between the stars at the speed of light, where we explore the universe not with our bodies but with our telescopes and our minds, where we search for life, for intelligence, for understanding across vast distances that we can never physically cross. It's not as exciting as science fiction, but it's real. And there's a beauty in that. A beauty in accepting the limitations of the universe and finding ways to work within them. A beauty in recognizing that we don't need to travel to the stars to explore them. We just need to look, to listen, to learn. So when someone asks how long it would take to travel 1 light year, the answer is both simple and complex. With our current technology, over 1,000 years. With near-future technology, perhaps decades to centuries. With far-future technology that might never exist, perhaps years. But the deeper answer is that maybe we don't need to travel 1 light year. Maybe we can accomplish everything that matters without leaving home. We can study the universe from here. We can search for life from here. We can expand our knowledge and understanding. From here, we can build a civilization in our solar system. From here, we can ensure humanity's survival by spreading to multiple worlds in our own solar system. We can create art, ATNCs, culture, meaning, purpose, all from here. And maybe that's enough. Maybe the stars don't need to be destinations. Maybe they can just be inspirations. Points of light in the sky that remind us how vast the universe is, how small we are, how much there is to learn and discover. 1 light year is an impossible distance, but it's also just a measure, a unit we invented to describe the space between stars. The distance itself hasn't changed. The stars have always been this far away. What's changed is our understanding. We've learned how far they are. We've measured the distance. We've done the math and realized just how long it would take to get there. And in doing so, we've learned something about ourselves. We've learned that we're bound to this corner of space. At least for now. We've learned that the universe is bigger than our ambitions. We've learned humility. But we've also learned something else. We've learned that even with these limitations, we can still accomplish remarkable things. We can still explore. We can still discover. We can still push the boundaries of knowledge. Just because we can't travel 1 light year doesn't mean we can't reach across 1 light year. Our telescopes can see across light years. Our radio dishes can listen across light years. Our minds can comprehend concepts that span light years. We've already crossed that distance in every way that matters, except physically. And maybe in the end that's the real achievement. Not building faster ships. Not finding loopholes in physics. But expanding our understanding to encompass distances we can never personally traverse. That's the human story. We're creatures who evolved on one small planet. Adapted to think about distances measured in miles and times measured in days, but we've taught ourselves to think about light years and millions of years. We've stretched our minds to encompass the cosmic scale. We've made the infinite comprehensible, and that's worth celebrating. So yes, it would take over 1,000 years to travel 1 light year with current technology. Yes, the stars are unreachable with anything we can build today. Yes, the universe is vast, and we are small and slow. But we're also curious and intelligent and persistent. We're also dreamers and explorers and learners. We're also the species that looked up at the night sky and asked, how far away are those stars, and then figured it out. We measured distances so vast they boggle the mind. We calculated travel times that span millions of years. We designed spacecraft that exist only on paper, but could theoretically cross interstellar space. We searched for planets around other stars and found thousands. We're searching for life in the universe, and maybe one day we'll find it. We've done all of this from one small planet using nothing but our minds and the tools we've built. And that's incredible. That's worth more than any physical journey could ever be, because the journey isn't about traveling 1 light year. The journey is about understanding what 1 light year means. The journey is about grasping the scale of the universe. The journey is not only about traveling through space. It is about looking up at the night sky with knowledge and wonder. It is about being here, in this moment, on this planet, and trying to understand the vast universe that surrounds us. That journey is about observing the cosmos and beginning to comprehend our place within it. And the remarkable thing is that this journey, the intellectual and spiritual journey, is one we can all take right now without traveling a single mile. So in the end, the real answer to how long it takes to travel 1 light year depends on how you think about it. For the body, the journey may take thousands of years, but for the mind, it can happen in an instant.